Alright, hello everyone. I hope you guys are doing good. So, first of all, I'd like to start by apologizing for being a bit inactive for the past few days. Well, the reason for that was for the first few days, I got sick, and when I got better, my laptop bailed on me. So, I was working with an old laptop which could barely turn on. So, it was really impossible for me to actually record anything. And so, yeah, that was the reason for me being inactive for around the past 10 days. And but now things are good. I have a new laptop and I'm all set. So yeah, I'll make sure that I'll try to be more regular, right? So with that, today I'm going to be discussing the solutions to Codeforces Round 770, which was held yesterday night. And I'll be discussing the first four problems from A to D. First of all, talking about the round, for me it was kind of like a nightmare. The round was really bad for me, but nevertheless, I am not going to complain about the quality of the problems. I think the problems were really good and they provoked you to think. And yeah, so nothing about the quality of the problems. The problems were good. Maybe they messed up a little bit on the order of the problems. Maybe C should have been before B, mostly because C uses a very standard idea, right? So yeah, that's my take on the round. The problems were good. B and C could have been switched. Problem D was very nice as well. And yeah, even though I got a minus 20, minus 120, sorry. So even though I got a minus 120, I am not complaining because these things happen. I knew a big rating fall was coming my way, but I just didn't anticipate it to be this big. But nevertheless, it's part of a much bigger journey. So I'll try my best to come back stronger in the next round. But with that in mind, let's start with the solutions. I'll be discussing the first four problems from A to D, and let's start with A. So in this problem, we have a string s of length n and a number k, and we will denote by rev of s the reverse of the string s. And what we can do is that we can apply any one of the following operations. We can replace the string s with s plus reverse of s, or we can replace the string s with reverse of s plus s. And what we have to tell is we have to tell how many different strings we will get as a result of performing exactly k operations. So yeah, this is the problem statement, quite simple to understand. So we have a string and we will denote its reverse by s prime, let's say. And what we'll do is we will do an operation k times, and in an operation we will choose one of the two things to do. We will either replace s with s plus s prime, or we will replace s with s prime plus s. And once we do this operation exactly k times, we need to tell what is the number of distinct strings that we can get. So let's look at the solution. It's not that difficult to understand. Okay, before that, I'd like to increase my font size to 20. Yeah, all set. So at problem A. Obviously, it's just a casework problem, and the first case that we'll make is that k is equals to 0. And obviously, if k is equals to 0, we have the string s and we do not apply any operation. So answer will always be 1. Pretty trivial to understand. So the second case that I make is that s is a palindrome. This is the second case that I'm doing. And I'm looking at this case because we are dealing with the reverse of s. So it makes sense to look at the case when the reverse of s is nothing but s itself. So this is the second case, and this is that s is a palindrome. So let's see what happens. So initially, what we have is s. So after we do the first operation, we have two choices. Either we append the reverse of s to the right of s, or we append it to the left of s, right? So let me denote the reverse of s by s prime. So after the first operation, I will get either s prime or s prime s. But since s prime is equal to s, both of them are the same. And both of them are nothing but s plus s is equal to 2s. So this is what I have, right? So this is what is happening after the first operation. Now let's look at the second operation. So I know that I only have one string which is 2s, and now I can either get 2s plus 2s prime, or 2s prime plus 2s. But the thing is that if s is a palindrome, then 2s will obviously also be a palindrome. And so This is again just one string and it's nothing but 4s. And so we can do the same thing for any number of operations, and what we notice is that after any number of operations we will get just one distinct string, and that's it. So we can say that the answer is always equal to 1. I can also show this after the third operation. So let's look at the third operation. Also give me a second. Alright, I'm back. So yeah, we were here. So when we look at the third operation, you can try it out yourself. You will always get just one string which is equal to 8s. So at the ith operation, you will get just one string which is equal to 2 raised per I times s. And so if s is a palindrome, we can clearly and confidently say that the answer is always going to be 1. Okay. So now that we are done with that case, let's look at the third case. So we have a general string s such that s is not equals to the reverse of s. Right? Okay. So now let's see what happens after any number of operations. So initially, we have just one string which is equal to s. So after the first operation, also let me make sure I'm recording. Yeah. So after the first operation, what happens is that I can get two strings, either s prime or s prime s. And I know that s prime is not equal to s, so I have two distinct strings. Okay. Now, after I do the second operation, what happens is that I can either choose the first string ss prime or I can choose s prime s, and then I can do two types of operations on both the strings. So I will get four types of strings, but I'm not yet sure that they're going to be distinct. So let's see what are the four possible strings we can get. So if we choose ss prime as our string and append its reverse to the right of it, we will get ss prime s prime s. If we append its reverse to the left of it, we will get s prime s s s prime. Similarly, if we choose s prime s to be our string, then we can get two possible strings, s prime s s s prime and s s prime s prime s. Notice that out of these four strings, only two are distinct. This first string is equal to this fourth string, and this second string is equal to this third string. And so there are only two distinct strings. Okay. But an interesting thing to note here is that both of these two distinct strings are nothing but palindromes. Why? Because s prime s is a palindrome clearly, and s prime s s prime is also a palindrome clearly. So both of these two distinct strings are palindromes, and we have already proved in case 2 that a palindrome will not produce any new string. And so, since both the distinct strings are palindromes, we will not get any new strings, any new distinct strings. Right? So the number of distinct strings will from here on be only 2. And so this is the entire solution. So if k is equals to 0, the answer is just going to be 1. And the second case is that if s is a palindrome, the value of k is immaterial, the answer is always going to be 1. And the third case is that s is not equal to the reverse of s. And in this case, since starting from the first operation, we have two distinct strings and the number of distinct strings is not increasing. So the answer is always going to be 2. And that's the solution. So let's just have a quick look at the code. So we have s as s and s1 as reverse of s. So the first case is if k is equals to 0, in that case answer is always going to be 1. Otherwise, if s is equal to the reverse of s, meaning s is a palindrome, again the answer will be 1, and otherwise the answer will be 2. So that's it. That's the entire solution to the problem A. And now let's move on and talk about the next problem, problem B. So yeah, this was a disastrous problem for me, and I was not able to make a very not so trivial observation. At least it was not trivial for me during the contest, and that is the only reason I messed this contest up pretty bad. So I kept on thinking, but I could not come up to the actual observation, and it wasted more than an hour for me. And actually, when I realized the entire solution, I felt pretty funny, and like the solution was very simple to code. It was just 2-3 lines, but thinking on that direction is the main thing. And sometimes you miss the small observations, and it's okay. It happens sometimes. So let's have a look at the problem. So the problem statement is involved, but what's happening here is that there are two people, Alice and Bob, and both start off with a number. Alice starts with the number x, and Bob starts with the number x plus 3. And we also have an array A of n integers. And what happens is that at every index of A, what happens is we have two choices. We can either XOR the number AI with our current number, or we can add the number AI to our current number. And both Alice and Bob do this process independently. That is, both of them can have different operations at different indices. Alice can choose to XOR her number at the ith operation, and Bob can choose to add it, and vice versa. And both of them can also do the same operation. It's totally up to them. So both their journeys are independent. Alice starts off with the number x, Bob starts off with the number x plus 3. And they have also provided us with the number y. And what they want to ask us is that if Alice starts with x and Bob starts with x plus 3, which among the two can end up with the number y? And they have also made sure that in the tests on which they will judge the problem, it is always the case that exactly one of the friends could reach that number. And so we just need to tell whether that person is going to be Alice or Bob. And that's it. That's the entire problem. And so you can see that there is nothing very trivial looking about this problem. And that is why me and a lot of people tried to complicate it, and we missed the fact that it's nothing but a division 2 problem B, and it has to be not that complicated. And that's a lesson for me and a lot of people there as well, that if you are doing an initial problem of a Div-2 round, then it's probably not that complicated. So now let's look at the solution. Okay, so the first thing is that Alice is starting with Alice is starting with x, and Bob is starting with x plus 3. So the first thing that we should do is that think something distinct about x and x plus 3. And if you think in this direction, then you'll probably end up thinking about the right thing. But a lot of people just ignored this fact and just thought that x and x plus 3 are simply randomly chosen values, but that's not the case. And the main thing is that x and x plus 3 always have different parities. And so this is the only thing which is quite distinctly similar, quite distinctly evident to the eye, that x and x plus 3 have different parities. And so it makes sense to think about the parities of the numbers. And so from here on, we will only think about the parity. So from here on, we are only going to think about the parities. And the parity is nothing but the 0th bit, right? So the parity is nothing but the 0th bit in the binary representation of a number. And so we are only going to look at the 0th bit of the numbers, right? We know that x and x plus 3 have different parities. Okay, and now we are only interested in the 0th bit. We will completely ignore all the other bits. So we are going to ignore all other bits. And the most interesting observation here is that the XOR operation and the addition operation are exactly the same if we are only looking at the 0th bit and ignoring all the other bits. So if we do this, the XOR and addition operations become exactly equivalent. And that's it. That was the main observation for this problem. And the reason is that our current there are really 4 cases: 1 0, 0 1, 0 0, and 1 1, right? And if we are only interested in the last bit, we are making 4 cases for the last bits. So if we are doing a XOR operation and an addition operation on two numbers which have these last bits, there are 4 possibilities. Then I'll just prove that the XOR and addition operations are the same. So if we have an addition here, both XOR and addition will give 1 and 1. And so if we have 1 0, both XOR and addition will give 1 and 1. If we have 0 1, again both of them will give 1 and 1. If we have a 0 0, both of them are going to give us 0. And this should be 1. So if we have a 1 and a 1, then the XOR operation is going to give us 0. And even the addition operation is going to give us 0, but the addition operation will induce an extra carryover to the next bit. But since we are ignoring all the other bits, we just care about what result we get on the first bit, on the 0th bit. And so what we notice is that the XOR and the addition operations are exactly equivalent if we only look at the 0th bit. And this greatly simplifies the problem. Now we just have to perform all the operations. It doesn't matter we perform the XOR or the addition, and we have to look at the parity. And what happens is that we start with x. So Alice starts with x, and I'm looking at the point of view from Alice. And so we start with x and we have to reach y. And if we only talk about the parity, initial parity is equal to x mod 2. Final parity is equal to y mod 2. And so what happens is that we have x mod 2, and what we do is for all the elements from 1 to n, we are simply adding them, because adding and XORing is just the same thing. So for the sake of simplicity, I'll just assume I am adding them. And so the change in parity is going to be nothing but the sum of all elements modulo 2. And this has to be equals to y mod 2. And so sum modulo 2 becomes equal to y minus x modulo 2. And so if this is the case, then Alice is going to win. And similarly, if this is not the case, then Bob is going to win. And the reason is that the value of x modulo 2 is different for Alice and Bob for sure, because Bob starts with the number x plus 3, which always has the different parity from x. And so here is the solution. The solution is a one-liner. So if sum mod 2 is equal to y minus x mod 2, Alice wins. Otherwise, Bob wins. And that's it. That is the entire solution to problem B. It was, at least for me, it was not that trivial, but it all depends on how you start this problem. If you at the beginning think about x and x plus 3 and parities, then you'll be able to do this problem in no time. Otherwise, you'll just get stuck on this problem, and that would lead to a rating loss of minus 120, and which was exactly what happened in my case. And so yeah, that's the solution. Let's have a look at the code. The code is super simple. You calculate the sum, and if s mod 2 is equal to y minus x mod 2, then answer is Alice, otherwise answer is Bob. And that's it. That's the solution to problem B. Now let's move on to problem C. And problem C is a pretty standard problem, I would say. There have been a lot of Codeforces contests even recently which use the similar kind of concept. So let's see. And that is why the number of solutions to problem C is much greater than a general problem C in a division 2 round. So I'll just briefly describe the problem statement. So the statement says that we have a matrix of size n cross k. We don't know what the matrix is. It actually is our task to construct it. And what happens is that we need to construct this matrix of size n cross k in such a way that we use every number from 1 to n into k exactly once. And also in every row, for every range that we choose, the sum in that range should be divisible by the length of that range. And that's it. We just have to output such a matrix. We'll be provided with n and k in the input. We have to first of all tell whether it's possible or not. If it's not possible, we just have to output no. Otherwise, we have to output yes, and also a valid matrix. So that's problem C. Okay. So the problem goes something like this. Given n and k, find a matrix of size n cross k such that each number from 1 to n into k appears exactly once, and also for any range in a particular row, the sum is divisible by the length of the range. That is to say, for any L comma R that we choose for a particular row, the sum of all the elements from L to R should be divisible by R minus L plus 1, which is the length of the range. Okay, now coming to the solution. So the thing is that this idea of sum being divisible by the length is not a very new one. It has come in a lot of CF contests in the past, and let's see how we tackle such problems. So the first thing is that we look at ranges of size 2. And once we look at ranges of size 2, what we want is we want their sum to be divisible by their length. Actually, the problem statement says that their average should be an integer, and average being an integer means that the sum is divisible by their length. That's why I didn't go by that statement. So yeah, average being an integer just means that the sum is divisible by the length, because average is nothing but the sum divided by length. So we look at ranges of size 2, and let's say there are two adjacent elements x and y. So we want x plus y to be divisible by 2 for all adjacent elements in every row, right? This is exactly what I want. But for x plus y to be divisible by 2, either both x and y should be odd or both x and y should be even. So I have established and I have proved that all elements in a row should be either odd or even. Because if a row contains both odd and even elements, there will be a location where an odd and an even element will be adjacent to each other. And if an odd and an even element are adjacent to each other, then their sum will definitely be odd, and that will violate our condition. And so all elements in a row should be either odd or even. So we can just categorize every row as an odd row and an even row. An odd row will have all the elements odd, and an even row will have all the elements even. Okay. Also, before that, there is a case which I forgot to mention. The first case is that when k is equal to 1. So if k is equals to 1, obviously there will be no range of size 2. And so we can just output, in the ith row, we can output the number I, and we'll be done, right? So output I for the ith row. And so the answer will always exist when k is equal to 1. We can just output I for the ith row. And so we'll just ignore that case, and we will assume that k is at least 2. And so if k is at least 2, all the elements in the row should be either odd or even. But this is nothing but a necessary condition. I haven't yet proved that this is sufficient. So now we will prove that this is a sufficient condition as well. Well, also, if we are just doing odd elements in a row and even elements in a row, there is no particular sense of ordering to it. So what we'll do is that we will put together only consecutive odd numbers and only consecutive even numbers in every row. So we will try to put consecutive odd and even numbers in every row. I should write it like this. Okay. So what I'll try to prove here is that if I do something like this, then I will always end up with a valid arrangement. And if I can prove it, then I'll be sure that this is a sufficient condition as well. So I would have proved that it is both necessary and sufficient, and so we'll be done. Okay. So the proof goes something like this. We know that if we put consecutive odd and even numbers, we are getting an arithmetic progression with a common difference too. So for every row, we will get an arithmetic progression with common difference 2. right? And we know that for an arithmetic progression of size n, the formula for the sum of all its elements is nothing but n by 2 times 2a plus n minus 1 times d, where n is the length of that sequence and a is the initial element and d is the common difference. And if I want this expression to be divisible by n, then essentially what I want is I want this particular expression in the bracket to be even, because if that is even, it will cancel out the 2, and then I'll be left with n into something which will be divisible by n, of course. So I want this expression inside the bracket to be even. I know that 2a is already even, so I want this thing to be even. But I know that n is not fixed, n is a variable, and I will get ranges with both even and odd sizes, so I can't do anything with n. But if I fix d to be even, then I'll be done. And here, this is exactly what I'm doing. I'm fixing d to be equal to 2, and if d is equal to 2, then Sn will always be divisible by n. And this is exactly what I want, right? I want the sum of all the elements to be divisible by the size of the range, and this is what I'm getting. And so this is a perfectly valid way. And hence I have proved that this is the necessary and sufficient condition as well. So this is the only way we can do it. Okay, great. But now we also have to discuss the case when it's not possible, and that's not very difficult to think about. So it will not be possible if n is odd. So if the number of rows is odd, it is not possible. And the reason is that every row is either an odd row and an even row. And I know that we have to use numbers from 1 to n into k. And so the number of odd numbers and the number of even numbers will differ by no more than 1. And so the number of odd rows and the number of even rows will have to be equal. The reason is that the number of odd and even rows should be equal. But if n is odd, then we can't achieve that. And so if n is odd, then the answer is impossible. And if n is even, what we can do is we can just output in every row consecutive odd numbers until we are left with no more odd numbers. After that, we'll start using even numbers. And that's it. That's the entire solution to problem C. It's impossible when n is odd. And also there is this case when k is equal to 1. In this case, we'll just output I for the ith number, for the ith row. So that's it for problem C. Let's just have a look at the code now. Okay, the code goes like this. First case, if k is equal to 1, that's simple. You just output I for the ith row. Otherwise, if n is odd, you output no. And finally, if n is even, what I have done is I have alternated between odd and even rows. So I have put my first row to be odd and the second row to be even. So in the first row, I'm getting 1, 3, 5. In the second row, I'm getting 2, 4, 8, and so on and so forth. So you can also see what's going on here. If you look at the sample tests, something like this is happening. In the first row, I'm getting all the odd numbers, and in the second row, I'm getting all the even numbers. And yeah, it's not very difficult to code it up. So yeah, that completes the solution to problem C. Let's now move on and let's have a look at the last problem that we'll be discussing, problem D. This was again a very interesting problem. I I was not able to do it during the contest, mostly because I was still trying to wrap my head around problem B. But yeah, this is problem D and a very good interactive problem. If you don't know what an interactive problem is, then I have already made a video explaining that, and you can check that out as well. I will link to it in the description. But otherwise, let's start with this problem. So according to this problem, we have a hidden array of n integers a1 up till an. And we know that there is exactly 1 0 in the array, and our task is to find that 0, as always. And as always, we will be given with a few queries. And here the number of queries that I can ask is 2 into n minus 2. And the most important thing is the nature of the query. So in the nature of the query, what I can do is I can give to the judge 3 integers, 3 indices I, j and k. All of them have to be distinct for sure. And in response, the judge will provide me with this. It will provide me with the difference of the maximum element minus the minimum element out of all the 3 elements that I provided, out of all the 3 indices that I provided. So here the judge will provide, I will provide the judge with ijk, and it will provide me with the max of ai, aj, ak minus the min of ai, aj, ak. And using such queries and using no more than 2n minus 2 queries, I have to output the position of the 0. The thing is that we don't have to exactly output the 0. Basically, we have to output two guesses for our 0, and we just have to make sure that the 0 in the array lies in exactly one of these two guesses. So yeah, we have to make two guesses, and we need to make sure that at least one of these two guesses is right, and at least one of these two guesses is the correct position of the 0. And that's it. That's the problem statement. I hope it's clear enough. And let's now look at the solution. Okay. So I'll just write down what we have to do. So we have array A having exactly 1 0, and we need to find its location, and we will have two guesses for that using at most 2n minus 2 queries. And in a query we will get max of ai aj ak minus min of ai aj ak, and that's the solution. That's the problem. So now let's have a look at the solution. Okay, so there can be various solutions, n number of solutions to this problem, and all of them involve some kind of casework. This casework cannot be avoided for this problem according to me, and so I will describe my own solution. So what I did was I made two cases in the beginning, and I will make these two cases and then I will go on. So instead of making cases, what I'll do is, first of all, we will fix two indices, let's say A and B. And once we have fixed these two indices, it makes sense to query for all the i's where I go from 1 to n, and the query will be of the type A, B, I. Obviously, I will not be equal to A and I will not be equal to B. I have 2n minus 2 queries, so that will utilize n minus 2 queries for me. But it makes sense to do this as a starting point, because obviously we have nothing else to do here, right? So we might as well fix two numbers and we query for everything else. So we will fix two indices A, B, and we query A, B, I for all I not equal to A and not equal to B. So this will utilize n minus 2 queries. Okay, now before we do that, we make an assumption, right? And so, what we need to find is the minimum element, but since we are getting the maximum minus minimum for every query, it makes sense to think about the maximum element of the entire array and the minimum element of the entire array. Obviously, the minimum element is going to be 0. And since we have two guesses, we might as well try to find both the maximum and minimum element and try to make sure that one of our guesses corresponds to the maximum element and the other corresponds to the minimum element. And so in this way, it makes sense to just think about the maximum element first of all. And so I will make my first assumption, and the assumption is that both max and 0 are not contained in A and B. That means it's not the case that A is equals to 0 and B is equals to max, or B is equals to 0 and A is equals to max. So I'm assuming that it is not the case. Later on, I will also tell you how to make sure that happens. But for now, I'm assuming that it's not the case that both 0 and maximum are in A and B only. So what I'm trying to say is that there is at least 0. There is at least one among 0 and maximum, such that it is not either capital A of A or capital A of B, where capital A is the array. Okay. I hope this is clear enough. So we are right now assuming that both 0 and maximum are not in the Ath index and the Bth index, or the Bth index and the Ath index respectively. So yeah, this is my assumption. Later on, I will also make sure that that happens. But right now, I'm just assuming that it is happening. And so I will try to do all these queries from I going from 1 to n, I not equal to a and I not equal to b. And okay, now let's see what's going on. So we have a number capital A of A and capital A of B. So without loss of generality, I'll just assume that A is smaller than B. Okay. So let's say this is A and let's say this is B. Okay. So we have A of A whose value is somewhere here, and then we have A of B. Without loss of generality, I'm just right now assuming that A of A is smaller than A of B. And I have also made sure that both A of A and A of B are not 0 and max. And so in a way, I have made sure that there are some elements at least here or at least here. It's not the case that all the elements lie in between A and B, right? So there will be at least one element either here or here to the left of A of A. Okay. Now, for any such element which does not lie in between A or B, what happens is that if I have an ith element here, what the result of the query is going to be nothing but A of I minus A of A. And if I have an ith element here, then the result of that query is going to be nothing but A of B minus A of I. Right, because I am always getting the difference of the maximum and the minimum elements. So if the ith element is here, maximum is A of I and minimum is A of A, and if the ith is here, then the maximum is A of B and the minimum is A of I. And so these are the two results. And obviously, if I look at the maximum query result that I am getting, I won't get it by any index I which is in between A and B, because if the number is in between A and B, then the result of the query is going to be A of I minus A of A. So out of these three values, obviously this third value can never be the largest because it is just corresponding to this much. But for any value which is either to the right of B or to the left of A, I am getting at least this range and also something extra. In this case, I am getting this result, and in this case, I am getting this result. And so I am at least getting this entire range from A to B, and I am also getting something extra. And so the maximum result that I will get will always be either this query or this query. It will never be from an element which lies in between A and B. And that's one thing. But also that maximum result, so if I'm getting the maximum result from an element I here, then that maximum result I will get only when A of I is the maximum element in the entire array, right? Because for any j which lies here, I will get a greater result for any I which lies here, right? So the more to the right I am, the greater my result will be. So as you can see from here, in this case, the higher the value of A of I is, the more my result is going to be. And similarly, if you look at the second case, I'm sorry, this should be minus. So if you look at the second case, if you want to maximize this value, then the value of A of I should be as small as possible. And we know the maximum value is max and the minimum value is just 0. And so let's say that we get the maximum query result at an index C. Okay. So we will be sure that A of C will either be the maximum element or it will be 0. So we can be sure that A of C will either be max or A of C will be 0. Okay. But right now we can't simply output the value C, because we don't know that a 0 will be there at C or not. We just know that either there will be a 0 here or there will be a max here. Also, we are able to make this, we are able to get this index C only because we made this initial assumption that both 0 and max are not included in A and B. So there will be at least one element here, and there will be at least one element either there or either here. And that's why we are able to make this assumption. Otherwise, if we don't make this assumption, we can't get to this conclusion. Okay, that's why this assumption is important. Later on, I will also tell how we can make sure this happens. But right now, we will make sure that A of C will either be the maximum or 0. Okay, so now we have three indices A, B and C. And we are sure that C is either 0 or maximum. And now the second, but now we don't know anything about the short location of 0. So we are not done yet. So now what we'll do is that we will query for all I. So we will query of the type A, C and I for all I not equal to A and I not equal to C. Right? So this is what I'm going to do now. And the reason for that is the reason for doing this is that I have the maximum or the zero with me. Also before that, for the sake of notation, I will denote the complement of 0 by maximum and the complement of maximum by 0. Okay, I hope this makes sense. So yeah, I have one of the values at the index C. I know for sure I have either 0 or maximum at the index C. So now what I'll do is I'll query of the type ACI for all I not equal to A and not equal to C. Remember that till now I have done n minus 2 queries, and if I do this I will do n minus 2 more queries. And by doing this, again I can divide everything that happens into two cases. So case 1 and case 2. So case 2 is this. So case 1 is that the complement of A of C is at A of A. And the second case is that the complement of A of C is not at A of A. I know that I know that A of C is either 0 or maximum. So the complement of A of C is somewhere there in the array for sure. But the two cases that I'm making is that the complement is at A of A and the complement is not at A of A. So the simpler case is case 2. So let's analyze it first. So if A of C is not, if the complement of A of C is not at A of A, then we will get an index I such that A of I is equal to A of C. So we will get an I such that A of I is the complement of A of C. And once I get that index, I know that either A of I is equal to 0 and A of C is equals to maximum, or A of I is equals to maximum and A of C is equal to 0. And so for let's say that index is equal to D. So we are getting an index D where A of I is equal to complement. And for that, the result of the query A, C, D is going to be maximum element only. The reason is that the max element is just going to be max and the minimum element is going to be 0, since I know that both maximum and 0 are present here. And so the result of such a query is going to be maximum, right? And basically that sums up what I'm trying to do here. So how to find out this element D? It's simple. So we will look for the index I, which gives us the maximum query result of the type A, C, I, and that I will be D. The reason is that if I get a query result, if I query for any index which is not equal to D, the result is going to be strictly smaller than the maximum element, because even if one of the elements is the maximum, the other element is not going to be 0. So the result of the query is going to be strictly smaller than the maximum element. So I can get the query result equal to maximum element if and only if I have both 0 and maximum. And I know that A is not equal to the complement of C, and so A is neither 0 nor maximum, and C is either 0 or maximum. So there will be a distinct index where I will get the maximum. I mean, it doesn't need to be distinct, but once I get such an index, I will be sure that both 0 and maximum are included in C or D. And so now I can confidently say that I am done. So I can just output C and D, and one of them is going to be 0 and the other of them is going to be the maximum. And that's it. So that's it for this case. We are done. But what about this case? So right now we assume that the complement of A of C is somewhere in an index which is not A. But what if the complement is in A only? Well, then all queries of type ACI will result in maximum. Why? Because the maximum element and minimum element are both present in A and C, and the result of all the queries are just going to be equal to the maximum. And so there will be only one distinct query result. So if all the query results are the same, then we can say that we are surely in this case, and so we can just output A and C. So we will output A and C, because we know that one of the elements from 0 and maximum is at C and its complement is at A. So 0 will be either in C or at A. So we will just output A and C. And by doing this, we have taken care of all the cases, and it looks like we have solved the problem. But not so fast. The thing is that we made an initial assumption that both 0 and maximum are not contained in A and B. So somehow we need to make sure that that happens. Well, it looks like we have done everything we can. How do we make sure that happens? But the good thing here is that we have just used n minus 2 plus n minus 2. So we have used n minus 2 plus n minus 2 equals to 2n minus 4 queries. So we still have 2 queries left. And what I'll do is I'll use these 2 queries, and I will take advantage of the fact that I have 2 queries left, and by doing that I'll make sure that the initial indices A and B that I'm choosing are not both maximum and 0 at the same time. And let's see what we can do. If you look at the constraints, you'll realize that the value of n is at least 4, and that's the best thing, and that's the good thing. So I'll make 2 candidates for A and B. So the first candidate is 2 and 3, and the second candidate is 3 and 4. Obviously, if one of them, at most one of them can be both 0 and maximum. Not both of them can be both 0 and maximum, right? And so I'm going to do that. Okay. So yeah, not both of them are going to be 0 and maximum. And just give me a minute. Okay, yeah, I'm back. So what I was saying was that at most one of them can be both maximum and minimum, because if both of them are maximum and minimum, then I'm sure that there are at least 2 maximums, and if there are at least 2 maximums, then I'm good. But if there is only one maximum, then we can have at most one of them to get to be both maximum and minimum. And so we will choose one of these to be my A1 and A2, and let's see how we'll do that. So what I'll do is I'll do 2 queries, Q1, which will be equal to the result of the query 1, 2, 3, and Q2, which will be equal to the result of the query 1, 3, 4. The thing is that if 2, 3 is equal to the maximum and minimum, then the result of this query, so if this is max and 0, the result of the query is going to be nothing but max. And if this is max and 0, then this is definitely not going to be max and 0. So the result of this query will be definitely less than max. So the point that I'm trying to prove here is that if one of them is equal to maximum and minimum, that is, if one of them is equal to maximum and 0, then the result of the query for that particular component is going to be strictly greater than the other pair. And so what I'll do is I'll pick that pair which will give me the smaller result. So if Q1 is less than equal to Q2, pick 1 and 2, or pick 2 and 3 as A1 and A2. Otherwise, pick 3 and 4. And that's it. So yeah, this completes the solution. Basically, the one which is not equal to 0 and maximum will always give us a strictly smaller query result. And if both the query results are equal, then that means that either both of them are maximum and minimum, in which case I'm fine, or both of them are not equal to maximum and minimum, in which case I'm fine as well. So if Q1 is less than equal to Q2, we pick 2 and 3, otherwise we pick 3 and 4. This way we will make sure that our initial assumption holds true. And yeah, this completes the entire solution. I know it's a bit complex, but I think it works. I think it was, the length of the contest was 2 hours and 30 minutes. I think that time was good enough to solve this problem, even though I could not. But yeah, that's it. That's the solution to problem D. Let's have a look at the code now. Okay, so I have A, B, C, D. I am initially querying from 1 to 3 and 1, 3, 4. If this result is smaller, then I choose 2 and 3. Otherwise, I choose 3 and 4. Then I'm going through the array, and if I'm not at A and B, I query for I, A, B, and I will look at the maximum result and also the maximum index. Okay, so now I have C. And now what I'll do is I'll query for A, C, I. Obviously, if I is equal to A or C, I'm not going to query. And I'll put all the query results in a set, and I'll also find the maximum index, that the index that gives me the maximum query result. Now, if the size of the set is 1, then that means I am in this case, that the complement of A of C is at A of A. So I will say that my two possible answers for 0 are A and C. Otherwise, my two possible answers for 0 are C and D, which are the two indexes that I was getting. And so yeah, this completes the entire solution to problem C, to problem D. And that is all that I had planned for today. Thank you so much for watching, and I will see you in the next one.